Welcome back, everyone. Today, we're diving straight into our explainer covering section 11.4 of your software engineering textbook, Programming for Reliability. Now, up until this point in the course, we've spent a whole lot of time looking at systems from a real bird's eye view, focusing on high-level architecture and design patterns. But today we're shifting our focus straight down into the actual code. We're going to master the universal rules of dependable programming. Because, honestly, at the end of the day, a brilliant architecture means absolutely zero if the code running underneath it is fragile.
Here is a roadmap for today's explainer. We're going to kick things off with an intro to dependable programming, then move into defending data and inputs, managing errors and exceptions, handling external threats and recovery, and finally, we'll wrap up with the concept of the pessimistic programmer.
All right, Section 1, Intro to Dependable Programming. Let's get right into it.
I want to frame our entire narrative today around one absolutely core concept: extreme pessimism. When you're writing dependable code, you literally have to treat your program like it's a fortress under siege. You have to assume the absolute worst about the environment it runs in, the data it receives, and the users interacting with it. And to build that fortress, we're going to rely on 8 universal guidelines for dependable programming. We've grouped them into logical buckets to make them easier to digest. Now, these rules aren't tied to Java or C++ or Python. Programming languages will constantly evolve and change, but these 8 principles, they are universal. Follow them, and you will drastically reduce faults across the board, no matter what language you happen to be typing in.
Moving on to Section 2, Defending Data and Inputs.
So this first logical bucket of rules is all about how we protect the program from internal data corruption and, well, bad user inputs. The crucial point here starts with guideline number 1, limit the visibility of information. Think of it like the military's need-to-know principle. Only the personnel who absolutely need a piece of information to do their specific job are actually given it. In code, program components should only ever have access to the data they actively need. We achieve this by using an abstract data type, or ADT. Simply put, an ADT is a data structure where the internal representation is hidden and all access is restricted to specific operations. So if we build a queue, we completely hide its internal structure from the rest of the program. We don't let anything know if it's an array or a linked list underneath. We only allow access through very specific, safe operations like put or get. This basically creates a firewall, stopping components from accidentally corrupting each other's data.
Next up is guideline number 8. Name all constants that represent real-world values. See, using what we call magic numbers in your code, like, say, multiplying a total by 0.15, is incredibly dangerous. I mean, what even is 0.15? It's totally ambiguous to anyone else reading that code. Instead, we use named constants, something clear like VAT_rate. By declaring a constant value just once at the top of your program, we completely prevent typos across thousands of lines of code. Plus, when the government inevitably changes the tax rate next year, our future system updates are instantaneous. We literally just change that constant in one single place, and the whole system is updated.
This brings us right to guideline number 2. Check all inputs for validity. Listen to me on this one. You must never trust user input, ever. You should rigorously validate inputs the exact moment they enter your program, and we typically use 4 main checks to do this. First, range checks. For example, a probability must always be a number between 0.0 and 1.0. Second, size checks. A bank account number must be exactly 8 characters long, no more, no less. Third, representation checks. A person's first name shouldn't contain any numbers. And finally, reasonableness checks. If an electricity meter suddenly reads 100 times higher than it did in the exact same month last year, it's highly likely to be a sensor error, not a genuine reading.
Okay, let's just pause for a slow, deliberate mini recap before we push on. To defend our data and inputs, we limit visibility using abstract data types. We completely eradicate magic numbers by using named constants instead. And we rigorously and strictly validate all incoming data to ensure it is completely safe before our program ever processes it.
All right, Section 3, Managing Errors and Exceptions.
In this second bucket, we're focusing on how a truly defensive programmer anticipates execution errors and internal system faults. Because let's face it, even with perfectly clean inputs, things inside the machine will eventually go wrong. Please draw a massive star next to this in your notes, as it is a crucial exam focus. Guideline number 6 is check array bounds. Now, an array is a sequential data structure with a fixed size. The massive problem is, older languages like C and C++ do not automatically check if an index actually exists inside that array.
So if you try to access the 15th item in a 10-item array, the program just blindly writes data outside the allocated memory. This is what we call a buffer overflow, and it is a catastrophic vulnerability. Hackers actively look for these to crash systems and inject malicious code. So always check your array bounds.
Let's define another really vital term here to set the foundation for Guideline 3. An exception is simply an error or unexpected event that happens during execution. Maybe it's a sudden power failure or the code accidentally trying to divide by 0. A dependable program should absolutely never just crash to the desktop when an exception happens. It has to manage the situation gracefully.
And that brings us to guideline number 3. Provide a handler for all exceptions. When normal flow is suddenly interrupted and an error is detected, a dependable system doesn't just halt and give up. It intentionally transfers control to a specific pre-written block of code called an exception handler. The system actively tries to recover safely, rather than just leaving your user staring at a totally frozen screen.
So what exactly does this handler actually do? Well, it typically takes one of 3 specific actions. Step 1, it might signal a higher-level component, basically throwing its hands up and saying, hey, I failed down here, you need to decide what to do next. Step 2, it might carry out alternative processing, attempting to fix the error and recover the system right then and there. Or Step 3, if things are truly beyond repair, it will purposely pass control to the runtime support system to execute a safe shutdown state. This ensures absolutely no data is corrupted as the program is forced to close.
Next up is Guideline 4. Minimize the use of error-prone constructs. Listen closely to this one, students. Some programming features are just famous for causing bugs, mostly due to simple human error. Floating point numbers, for instance, often lose precision, making direct comparisons completely unreliable. Dynamic memory allocation relies entirely on programmers remembering to free up space manually, which very often leads to memory leaks that slow down the whole system. And pointers, well, they can easily be mismanaged and point to the completely wrong memory address. You should really avoid these error-prone constructs unless they are absolutely necessary for your system's performance.
Time for another quick recap. To manage internal errors, we always check array bounds to prevent catastrophic buffer overflows. We provide handlers for all our exceptions so our program never crashes unexpectedly. And we deliberately minimize the use of notoriously tricky, error-prone constructs.
Let's move into Section 4, External Threats and Recovery.
Our final bucket of guidelines deals with external components failing and how we protect hours of computational work from just vanishing into thin air. Definitely flag this one for the exam as well. Guideline 7 is include timeouts when calling external components. Imagine your program asks a remote server somewhere across the internet for some data. If that remote server has suddenly crashed, your program shouldn't just wait around indefinitely. If it does, the user experiences what we call a silent system failure. The screen just freezes forever with no error message at all. Instead, you set a timeout. If the server doesn't reply in, say, 5 seconds, your program automatically assumes failure, it takes back control, and it handles the situation safely. To introduce our final rule today, we need to understand exactly what a checkpoint is. A checkpoint is simply a saved copy of data or the system's current state. If everything goes terribly wrong, we can use this saved checkpoint for backward error recovery, effectively rolling the entire system back to the last known safe state. And this perfectly underpins Guideline 5, Provide Restart Capabilities. If a user is filling out a massive multi-page e-commerce form, or if your software is running some massive scientific computation that takes hours to complete, a sudden power crash shouldn't wipe out all that hard work. By continually saving checkpoints in the background, your program can provide a restart capability. When the system comes back online, it picks up right where it left off just before the failure.
Let's quickly summarize this final bucket. To handle external threats, we include timeouts so we aren't left waiting forever on dead servers. And we provide restart capabilities using checkpoints so our users never lose their hard-earned progress. And that completely wraps up our 8 rules of dependable programming.
Finally, Section 5, the pessimistic programmer.
All right, let's bring this explainer to a close and transition into a comprehensive summary of today's lecture by fully embracing the mindset of the pessimistic programmer. Here are your final, crucial study pointers for the exam. First, you must be able to list and fully explain all 8 dependable programming guidelines we covered today. Second, you really need to understand the cause and effect. Missing array bounds checks directly causes buffer overflows. Third, missing timeouts when you're calling external components causes silent system failures. Truly understanding these low-level code vulnerabilities is absolutely critical before we move into our next topic, where we'll be zooming back out to look at fault-tolerant architectural patterns.
I want to leave you today with this final, provocative thought. Writing dependable code is an act of extreme pessimism. You must assume every input is wrong, every external server will crash, and every array will be pushed past its limit. If you program with this exact mindset, literally anticipating failure at every single turn, you won't just write code, you will engineer truly resilient, unbreakable software. Thank you so much for joining me for this explainer, and I will see you in the next lecture.